Stanford-based. He's also in Portsmouth University. He's going to tell us about CMB, parity, and quantum gravitational physics. So,
thank you, Carlos. Okay, well, so as you know, the cosmic microwave background is one of our key views into understanding the evolution of cosmos. Is a relic radiation from the time when the first atoms were formed. And it has provided, especially thanks to 3 satellites, COBE, WMAP, Planck, but also balloon observations from Earth, an exquisite view of the early universe. And it gives us a measurement of the angular power spectrum of temperature fluctuations in the CMB, give us a view of acoustic oscillations that can be traced to the origin of the seeds that create galaxies that we see today. So this is our standard model for cosmology. Looking at this power spectrum of the cosmic microwave background, we can also deduce cosmological parameters like how much dark matter there is, how much diffuse or baryonic matter there is. You can also, by using a model, measure other cosmological parameters, for example, the rate of expansion of the universe, and also even the acceleration of the universe through knowing the distance to that cosmic structure and typing together all these cosmological parameters. So it's a pristine view of the universe. And maybe if you are not familiar with that, this is giving us very detailed information, so independent modes for thousands of, few thousand of multipoles. I'll show you some of these now. So it has a lot of information, very high signal to noise, a lot of constraining power for cosmology. And it gives a very nice match to a very simple cosmological model that has a few parameters. How many depends exactly which flavor of the model you take, but a few, say 7 cosmological parameters. That is very nice because with a few parameters, you can explain a lot of the cosmic evolution, and you can also explain this cosmic microwave background. And these, the values that we obtain from looking at the cosmic microwave background agree with many other observations that we see in the nearby universe, and also by interpreting the nucleosynthesis, the primordial nucleosynthesis of elements, by looking at stellar evolution, how stars forms, what is the yield of metals, and etc. So it gives us a coherent picture of the universe with just a few parameters. But as you know, it also happens every time you resolve a problem, you open 1,000 more, right? So it also opens problems. One of them is to understand those parameters, what they mean, why there is dark matter, what is dark matter, is there dark energy, what is dark energy, etc. So this, we are working on trying to understand that with better observations and with better models, etc. Well, this is my introduction without any pictures, but I imagine most of you know all of this, but I'm just making a brief summary. And I'm going to be focusing on something called anomalies in the cosmic microwave. And I'm going to mention these anomalies. And so these anomalies, the ones I'm going to focus on, so the model fits very well. It gives very good chi-square. But there is a region of the model which is on the very largest scales, where there are some tensions between the best fit model and the observations. And these tensions are called anomalies. It turns out that on very large scales, we are dominated, I will mention, by something called sampling invariance, which is the fact that we only have one universe. And so when you look at very large scales, you only have a few independent observations of very large scales. And so where these anomalies are more important is also where the errors are bigger. So in the region of smaller scales, where we have a lot of information, we don't find these anomalies. We only find these anomalies on the region where the errors are large. So this has also made some people skeptical or more or less ignoring these anomalies for a long time, but they have been there for the very beginning of the observations. And I will mention a few of them. And I'm going to focus in one anomaly that you might have not heard about, although is known, it's not a new result, which is an anomaly in the parity of the measurements. And my focus is to explain you what this means, what I mean by that. Why is this an anomaly? And what we have found two interesting things. One is that the parity anomaly explains a lot of the other anomalies. So there is a connection between these anomalies, and they can very nicely be explained with the parity anomaly. And then I'm going to tell you what we think this parity anomaly means. And this is evident for quantum gravitational physics, new evidence for quantum physics on the cosmic microwave. Okay, so let me go on with, need to click, and maybe okay, very good. So what is parity? What is parity? So it's very simple. Remember when you study the hydrogen atom, right? That in chemical, I was told about this in chemical course, that you decompose the spherical, something that has a spherical symmetry, you can decompose in spherical harmonics. This is used in many aspects in astronomy and in physics. One such decomposition, so basically what you have here, I don't know if this, yeah, can you see the point? So this is the temperature of that we measure of the cosmic microwave background. So in the cosmic microwave background, basically what we measure is the intensity of light at some frequencies, and you can convert that into temperature. So these are temperature fluctuations. So this is a dimensional in the sky. N is just the position angle in the sky. And the cosmic microwave background comes from a very thin layer. So it comes from a given time, which means a given position around us, right? Because the time is basically the time light has taken to reach us from that position, which is most of the age of the universe, the cosmic microwave background, with respect to the Big Bang, whatever the Big Bang is, and I will also talk about this a little bit. The cosmic microwave background, the first atoms were formed about 300,000 years after the Big Bang, whatever the Big Bang is. And then after that, the light from this cosmic microwave background has been traveling to us for about 14,000 million years, okay? So, but this, what we see, these temperature fluctuations are very small, one part in 100,000, one part in 10 to the 5, fluctuations in the temperature at different positions in the sky. And I'm going to show you these maps. So that's what we measure. And with the latest data from Planck, we are able to measure these fluctuations on very small scales of a few minutes in the sky. So we have thousands of points of these fluctuations there. And I will show you the map, and I'll try to explain what they mean. So why there are temperature fluctuations? So basically, if the metric is not just homogeneous, but there are perturbations in the metric at that time, this, because of gravitational redshift, this is called the Southworth effect, the photons that come from a place that has a slight overdensity will change the temperature because they need more energy to escape from that position in this sort of scattering. Whereas if it is a void, it will be in the opposite direction. So temperature fluctuations map density fluctuations in the surface of last scattering. So when we map this, because it doesn't have radial dimension, it comes from a very thin layer. So basically, when the universe becomes transparent, these photons are free to arrive us, and they all come from the same surface, right? So it means we only have 2 dimensions to describe this, which is angles in the sky. And because, so then the way we describe angles is with this spherical harmonics. So this is basically a Fourier decomposition, but instead of being 2D Fourier compositions, is a decomposition in a sphere. And basically, the YLM is the function we are used to do the composition. This is, for example, L equal 1 is the dipole. So it's basically half a sphere yes, it's a dipole, right? The cosinus in the sky. L equals 2 is the quadrupole, and this is how the quadrupole looks like. I just put the quadrupole and the octopole. So you can see L, which is the multiple, gives you one of the two numbers by which you describe these harmonics. And the other number, the M, is like the orientation, is related to the angle in the sky. So then here you have L equal 2, these are the quadrupole. For each L, you have M goes from minus L to plus L. So then you have 5 different orientations for this quadrupole, right? And you can see immediately, this is the same for the octopole. So the difference then between the quadrupole and the octopole is like in Fourier modes. It's like you divide first. The first is you divide, imagine a wavelength in a box. So the dipole will be a cosinus. The quadrupole will be to have a wavelength that is half of that one. Then the octopole will be half of that one again. So each multiple halves the wavelengths, and then you describe your harmonic. The composition will be like a Fourier space, the composition into Fourier mode. So each multiple is a Fourier mode. And you see here the quadrupole has lower frequencies in the sky, but not the big difference between these two. This, when L is even, you have this so you have this rotational symmetry, which is symmetric, right? For example, you see this part is symmetric with that part, whereas when you have L equal odd, you have antisymmetry, right? So the even multiples are symmetric, whereas the odd multiples are antisymmetric. And this is the parity, right? So basically, not all, we have all these multiples that go in the, for example, in the Planck data, we analyze the multiples from 0, which will be the monopole, 1, the dipole, 2, the quadrupole, 3, the octopole, and we go all the way to a few thousand, right? And these few thousand, then you are doing this Fourier decomposition of very small scales. So this is how we analyze these maps. The power spectrum that I mentioned before, that we feed to the models and give us this nice spectrum with the baryon acoustic oscillations and this information about the physics of the cosmic microwave background. The power spectrum is just taking the amplitude. So these are the coefficients of the Fourier modes. So this would be like the delta K or the K modes if you do a regular two-dimensional decomposition. That's basically ALMs, where L will be the absolute value of K of the mode, and M is the angle, the vector of the mode. Basically, that's the way to think about this. And the power spectrum is just taking the Fourier, these modes, and taking the modulus and the square, and then sum for all M's. Why we sum? We average for all M's. Why? The reason we average for all M's is because we are assuming isotropy. If you assume isotropy, then you can combine the different orientations to have more power in your measurement, right? Because the power in your measurement is how many of these you combine. If you just have one mode, you have a lot of error. So because when the number of M's depends on L, this is the number of L's, is 2L plus 1 is the number of M's. So this is the average. When L is small, you are averaging, for example, for L equals 2, this is 5. That's the 5 you are averaging. So you are only averaging 5 numbers. When L equals 3, you have 7 numbers. You are averaging 7 numbers. So basically, this is the information we subtract. when L equals 2,000, you are averaging 4,000 numbers. So then the error depends on this, how many modes you have. So for the lower multiples, which is the largest scales, so for example, the octuple, the quadruple, what this means, this figure, what it means is that you divide the sky, the full sphere, in 4, basically 90 degrees. The dipole will be divided in 2. When you divide in 2, you have 3 independent orientations, which is the 3 axes. So when L equals 1, you have 3 multiples. So you can only average 3 numbers. When L equals 2, you have 5, you average these 5 numbers. And basically, this corresponds to angles roughly of 90 degrees. The multiple, the octuple, will be roughly of 40 degrees, 45. The next one will be 45 over 2, etc.
Enrique, sorry to interrupt you. Are you still on slide 2? Because I'm not sure you are.
Yes.
I can see it in here. Okay, you're still in slide 2. Good.
I'm going very slow, Juan.
Sorry.
I'll try to speed up. I don't know if I'm going to slow, probably. I don't know if you have seen this before. This is totally trivial. Anyway, just in case, I want to make very clear what I mean by parity. And this is what I mean by parity. The parity, what I'm going to tell you, is that the modes that are even look different from the modes that are odd. And what this is telling you is that when you look at opposite directions in the sky, the symmetry is broken. You choose a parity, you choose a symmetry. And I'm going to specify this more. Let me mention, this is the power spectrum. Another way we look at that is the 2-point function, which is basically just taking the temperature in 2 different positions in the sky. You multiply, and then you average for all pairs that are the same separation. So again, this involves assuming isotropy. So we are always assuming isotropy when we do power spectrum. This is assuming isotropy. Here, assuming isotropy is going from here to here, that the correlation does not depend on the direction between the 2 pairs, but only depends on the absolute distance between the 2 pairs. Then we average all possible angles. So there is a relation between the 2-point function and the power spectrum, which is very well known in statistics, is the Percival relation, which is basically the one given by Fourier transform. The power spectrum is a sum with a legendary polynomial of, the sum of the power spectrum gives you the 2-point function and the other way around. So the integral of the 2-point function gives you the power spectrum. So these are like, you can look in Fourier modes or in real modes, but you basically, in one way, you are looking at angles in the sky, and in the other one, in the multiples, you are looking at wavelengths, so modes in the sky. Okay. In particular, one thing of interest is the 2-point function when these 2 points are at 180 degrees. So I will call these antipodes. So you just choose any direction you want in the sky, you look there, and then you look in the opposite direction. Then you multiply the 2 temperature fluctuations in these opposite directions, and you take an average of all of them, and then you see what you get. This is a measure, this product, without the average, the product of these antipode temperature fluctuations is a measure of parity. Because if the parity, if there is no parity, you expect this average to be 0. If it is symmetric, you expect this average to be positive. If it is antisymmetric, you expect this average to be negative. What this means, it means that when you see a fluctuation in the sky to be in that direction positive, you expect that in the antipodes, it will be negative. That is antisymmetric correlation. If it is systematically positive, it will be symmetric correlation. Okay, so this is what I mean by parity, and this is what we are trying to understand here. Okay, let me show you this in one of these maps. This is a typical way we project the Earth. So I took this map with the levels of elevation on Earth, including sea elevation and Earth elevation. So red means positive elevation, blue means negative elevation. If you take a parity conjugate of this map, what it means is basically that you look at a parity conjugate means that I'm going to flip and put the value that I see in one antipode, I flip it to the other side, to the antipode, right? This is just to show you where the antipodes are. For example, the antipode of Barcelona here, you can see Barcelona there. If you go here, you can see where the antipode is. It is basically New Zealand, right? Somewhere close to New Zealand. This is because these maps are tricky. When you want to see these antipodes, they are, you see, they are basically, you have to learn how to do that. This is like 30 degrees. You have to move like 6 of these spots to find where the antipode is, just to train your eye. And what I done here is I show, this is basically here, you have it here. Any map that you have can be decomposed into symmetric and antisymmetric maps. This is a property of any scalar field, and this is trivial to show. Basically, the antisymmetric map is just the sum of the map minus the antipode map, whereas the symmetric map is the mean of the map and the antipode map. So basically, it means that any image you have in the sky, you can decompose into antisymmetric and symmetric components of that image. And this is what I've done here. This is the antisymmetric component of Earth, and this is the symmetric component of Earth. How you interpret that? Well, the poles are symmetric. You can see it here, because there is elevation in both sides of the poles, right? But there is a big antisymmetric region here that shows in blue, because blue means negative. When the product of the map with the antipode is negative, it means antisymmetric. So you see, what is this? Why there is this? Well, this is the antipode of Australia, is the deep sea of the Atlantic. So this is an antisymmetric fluctuation. So we can, by using these maps, we can clearly see whether the maps are symmetric or not. And this is basically what we've been doing. So first, I'm going to try to convince you that I can see these asymmetries in the cosmic microwave background by naked eye. And then I'll give you the formal statistical results, which are more accurate and more precise. But I think the cool thing about this is that you can actually see this by eye. You don't need to do fancy Bayesian statistics. You just look at the maps and you see that it's antisymmetric. I want to convince you now, every time you see the CMB, you will see that it's antisymmetric. After this, if I convince you. Okay, so this is the cosmic microwave background. This is how it looks. This is the actual sky that we see. And as I was telling you, here I put the fluctuations in terms of sigma. This sigma is the RMS fluctuation. And this is this value that is about 10 to the minus 5. So it's very, very small fluctuations. So it's very homogeneous. It has a uniform temperature. And then there are these various like inhomogeneities of 10 to the minus 5. And I have smoothed the map so that you can see with the naked eye. And basically I smooth it with 1 degree, which is roughly the scale of these acoustic oscillations that we measure in the power spectrum. So these blobs that you see here are the baryon acoustic oscillations that we see in the cosmic microwave background. And now this is the first time I see it done, is what we did in our paper. By the way, I didn't mention that this is work that I've been doing with Shravan Kumar, who is a Newton Fellow in the Institute of Cosmology and Gravitation, where I, as Carlos mentioned, I am on sabbatical leave. And this is a work we've done that has been published, and the reference has been given in when the seminar was announced. It's in GCAP. Okay, so now we take the CMB and we decompose into symmetric and antisymmetric, because we know how to do it. It's very simple. There are several ways to do it, but it's totally straightforward to do this composition. So basically, we're doing this. The antisymmetric part is you take the map and you subtract the antipode of the map. And this is what you see. This is the antisymmetric map of the cosmic microwave background. And by construction, this is antisymmetric. Okay, just by construction. So for example, you can see it here. This is a very large cold spot, C1, and the H1 will be the hot spot corresponding. Because of the projection, they are a bit deformed, but they are exactly antisymmetric regions in the sky. So you can see, you can train your eye to see, oh, this very cold spot here, it appears there as a hot spot just by construction. There is nothing new here. This is normal. It's just to train your eye on how to see antisymmetrics, right, in this kind of maps. Here, this one is in microkelvins. So this is 10 to the minus 6 Kelvin. The mean temperature is 3 Kelvin. So this is showing that the temperatures are very, very small variations. Now, the issue with these maps, so I don't like using these maps because in the middle of the map is the galaxy, right? So you have to be very careful because most of what your eye is seeing is the galaxy, not the cosmic microwave map. So it's a bit misleading to look here because we don't know how much of this is contamination from our own galaxy. Of course, the Planck team and the CMB people are very smart. They have many frequencies. They have very careful techniques to subtract that. And this is the best you can do. There are several ways you can do that. So there are different component separation methods. And then you can compare different component separations and everything. But you always wonder if what they've done might have still some residues from the galaxies, and definitely there are. So you shouldn't trust this kind of maps. So I'm going to show you a different projection from this. This is just mentioning that when you introduce the mask, we use this parity mask, which is a mask that has been symmetrized so that you don't introduce parity with the mask. So basically we symmetrize the mask. This is just a technical step for what we're doing with the statistics. So all the statistics I will show you when I show you numbers are with this mask. Very conservative, symmetric masking. And then the only place where we can look for symmetry or unsymmetry is outside these masking regions. Okay, this is the way you should look at CMB maps. It's more boring, maybe, but if you look at the north and south galactic caps, then the galaxy is 1 millimeter here. You don't see it. If I put the mask there, you wouldn't be able to see that. Because it's going perpendicular. So most of the galaxy information is gone. And now you see the CMB. This is the real CMB map. I call it SBICA because it's one of the component separation that are officially released by the Planck team. We have used 4 different component separations and done all the analysis with different component separations to make sure that the analysis don't depend on that. And they don't, because all our analyses are dominated by this thing here that we call cosmic variance, by how many modes you can average. And because I'm going to be talking only about the first few multiples, they are all dominated by these sampling errors, which is much bigger than any issues with the component separation once you remove the mask. Okay, so this is how it looks. This is the cosmic microwave background fluctuations in the sky, looking north and south of the galactic cap. And now this is the antisymmetric map again. So the composition, now you can see the antisymmetric here. For example, this fluctuation, which is a Barça t-shirt, right? Here becomes a Madrid t-shirt on the antipode. This is by construction because it's the antisymmetric part of the map. There's nothing new or interesting in this map, other than you see a Snoopy here, right? And then Snoopy is here backwards. And the only reason it's backwards is because when you look at these things, they are like if you put 2 halves of a sphere and then you fold them together in one. So you see it flipping. But I will flip it for you. I will flip that so you can see exactly the parity things. Okay. Now this is SMICA, and now this is the CMB map, north and south, where I took the antisymmetric regions that I randomly draw here. You can do something far more smart with techniques to find excursion sets and images if you want, but here I've done it by hand, just to put some nice thing. This is the Barça with the shield, and this will be the Madrid with the shield, right? Now, this is the real map, not the antisymmetric map. You see the Barça t-shirt is here and the Madrid t-shirt is there. You see here a positive fluctuation, here it's a negative fluctuation. So for most of the maps, just by eye, you can see this is not 100%, it's just a fraction, but there is an excess of antisymmetric structures on very, very large scales. There are exceptions, for example, which I have put, I'll show you the exceptions later. Let me flip the map so you can see it better. Now I have flipped the south, and when you look for antipodes, now you just look at the same position in the sky. So you see here the Barça t-shirt with the shield of the Barça, and here's the Madrid in the opposite side of the sky. This is the real CMB. This is not manipulated in any way. So just by naked eye, there are some exceptions I put here in gray. For example, here there is a hot spot that here, well, it's a bit lower, but it's not blue. So there are regions that don't follow this, so it's not 100% antisymmetric, but statistically it's very significant, so much so that you can see it with your naked eye. That's the point I want to make. So now, this is my test with the normal maps. So let's see if I convince you with this. Now, when you look at this, this is the CMB, this is the antisymmetric CMB, and this is the symmetric. So these are the sum of these two gives you that. It's just a decomposition of the CMB. Now, if you squint your eyes, tell me which of these two looks closer to this. It's obvious. And this, yes, squinting your eyes a little bit, you're doing a Fourier transform when you squint your eyes, right? And then you immediately see the antisymmetric is much closer to the real, even with your eyes. There is no magic here. I haven't done anything. Now let's look at the statistics of this. For example, this is the 2-point function. So this is the correlation between temperature fluctuations in the sky as a function of angle. And what you see here, the blue is the measurement. This is 1 sigma, and this is 3 sigma contours for the measurements in the CMB maps. And what you see here is the 180 degrees, the antipode, has the same correlation as 0, but with the opposite sign. You see that? So this shape tells you that is dominated by antisymmetric correlation. This is just statistics. Now, this is the prediction of the Landau-Koldal matter, is the black line. The prediction of Landau-Koldal matter is not antisymmetric, it's more symmetric. The reason why it's symmetric is because the prediction comes from inflation, and inflation has a scaling by the spectrum of fluctuations, which means it has the same power on all scales when you put it in the right units, okay? So the Landau-Koldal matter model predicts fluctuations on all scales, including this. And the reason it has this funny shape is just because when you project in the sky this scaling by and power spectrum, you get this legendary polynomial, and they have these funny shapes here. Now, the blue is the symmetric part of the black, and the red is the antisymmetric part. So if you decompose the theory into symmetric and antisymmetric, the antisymmetric part of the theory resembles very much the data, right? And this is the main result I want to show you. I'm going to show you this result in different ways. Now we can look at this in Fourier space. But let's pause for a minute and ask, why is it possible that there are antisymmetric parity conjugate regions in the cosmic microwave background? How is that possible? For one thing, these regions, any region that is bigger than 1 degree, are what we call in cosmology super horizon, which means that they have, at the time of the CMB, these fluctuations are separated by distances that are larger than the horizon at that time, which means the horizon is the distance traveled by light in the age of the universe. or given the rate of expansion of the universe at that time. So these are very large fluctuations that are super horizon. What does this mean? If they were even, maybe you could think of a non-trivial topology that relates there, or even of inflation that connects fluctuations on super horizon scales with this scaling variant spectrum and tells that fluctuations have to be correlated, but even not anti-correlated, right? And I will briefly mention, because I spent a lot of time trying to explain the basics, just briefly mention two things that are interesting to understand that. One is the strange wall of horizons, which is the fact that the speed of light is constant. And the other one is the strange wall of the quantum wall, which is the fact that h is a constant and is not zero. So basically, these two things are just saying that physics is finite. Finite the speed of light, finite action, finite uncertainty. So in the terms of horizons, what I want to mention here is that, just to be brief about that, when you look, this is the scale factor, which is time, and this is a physical scale in the universe. So when you look at how scales evolve in the universe, when the universe expands, scales grow with the scale factor. So here, it will be some line like that. Whereas the expansion of the universe nowadays is faster than how scales grows. So the horizon grows faster. And the green line is what we can observe. So the cosmic microwave background in this picture will be here. And so we see super horizon fluctuations that are, we believe, created by inflation, and they are larger than the horizon. And but the interesting thing is that the fact that the speed of light is constant creates these horizons that help us understand the physics of what we are seeing. And the red line is an horizon that is given by the cosmological constant. As you know, when we measure the rate of expansion of the universe, we find that there is an additional constant that we call the cosmological constant. And that constant creates an horizon. And basically, if the rate of expansion is given by that, it's telling us that no light, nothing can be, will ever escape this horizon, the red one. And this is what we can observe. So, of course, that's the same thing I'm saying. We cannot observe anything outside this horizon. But when we look at the cosmic microwave background, we are limited to this region. On scales larger than 1 degree, we are in the blue part. On scales, sorry, smaller than 1 degree, we are within the horizon. And on scales larger, we are in this yellow region. So usually in cosmology, we interpret the expansion of the universe and the metric as being a global solution, which means it's an infinite universe. But because we have measured lambda, this infinite universe here that has the same density everywhere is very hard to explain physically, because these regions that are outside here are not causally connected, okay? So what this means in practice, this is this idea that I mentioned here before, this one of the talks, the black hole universe, is the idea that outside this region that is not causally connected to our universe, if you assume that this region is empty, rather than being the same density as our density now, which is the standard model, then what you have here is a black hole, and we are living inside the black hole. Now, why suddenly go from parity to black hole? This is just to tell you that the fact that we have horizons indicates that depending on what is the origin of these fluctuations that we see in the cosmic microwave background, you can actually have a cutoff on this scaling variant spectrum. And we believe that some of these anomalies could be related to this cutoff. And I'll mention this in a minute. Let me now mention the strange world of quantum mechanics. This idea that h equals 1 created the Schrodinger equation. And for this talk, because I have talked too much already, the only thing I'm going to say is that the standard Schrodinger equation which is basically this one, is a linear equation. Without this, instead of being a matrix, this will be the Hamiltonian. That's the standard Schrodinger equation that you learn at the school. And this equation is not CPT. It doesn't have parity. So usually there are these discrete symmetries that you can flip time and you can flip the parity, the positions. All the laws of physics, because they are quadratic, has this CPT. C will be the charge conjugate, but let's talk about PT now. We expect that the laws have this PT symmetry. There is no principle, it's just a symmetry that the laws have. The Schrodinger equation does not have PT symmetry. It chooses one direction of time because it was invented at the time when it was classical, not relativistic. Then there was a relativistic version of that, but it started with something that does not respect PT symmetry. And what we have done here is to extend the Schrodinger equation to have this PT symmetry. Okay. When you do that, then now what happens is that if these fluctuations that we see in the CMB are originated by quantum fluctuations from something like the Schrodinger equation or the more fundamental quantum field theory that comes linked to this equation, then the PT symmetry is broken by the expansion of the universe. The expansion of the universe is, it breaks P symmetry because it gives you an evolution, a time, an arrow of time. And this asymmetry in time breaks this asymmetry in parity. So if you believe that PT should be respect, which is what we see in all the laws of physics, the fact that the universe is expanding and you think that the perturbations in the cosmic microwave background are primordial related to quantum mechanics, then this is what we propose in our paper, you can explain the parity asymmetry by the breaking the time asymmetry. And in fact, you can actually make a prediction without any free parameters for that. So you can actually replace the standard prediction of lambda for dark matter, taking into account this without any new free parameters. So I'll show you the results of that. Well, basically, this is technically the equation. It basically predicts different power spectrum for all odd and even modes. Remember that this means that there is an antisymmetric component here. Because it's not the same in odd and even, is lower for even modes and higher for odd modes. And this is what creates, we believe, is a conjecture, right? This parity asymmetry that we're seeing in the cosmic microwave environment. So we believe it's something very fundamental. Let me show you how this looks in the power spectrum. This is the power spectrum for the first multiples. This is what you expect. The blue line is what you expect for lambda cold dark matter. And this is what you actually measure. You notice something here? It goes even odd, even odd, even odd, up and down, up and down, up and down. And so the L equals 3 is even. And according to this prediction here, if you have even, it has lower amplitude. The nice thing of the prediction is that we can predict this quantity, the asymmetry, and only depends on the same parameters that are used in inflation. So the same ones that you feed on the smaller scales to the power spectrum.
L equals 3.
Sorry, what did I say?
L equals 3.
Is odd. L equals 3 is odd. No, L equals, sorry, L equals. Excuse me. The one I was showing is the quadruple, L equals 2. So L equals 2 is even, and this is why it's lower. It's the first multiple. So we measure the monopole, which is just the temperature of the CMB, the dipole, which is divided in two, and we believe this is related to our flow. It's called the dynamical dipole, which is because we are moving, we see a dipole in the CMB, and this dipole is much larger than 10 to the minus 5. It's like 10 to the minus 3, and it roughly agrees with the movement of our local universe. So this means that it's very hard to measure the primordial. So the first thing we measure is the quadruple, which L equals 2, and it's even. And this model predicts that the quadruple should be lower. But it predicts by how much? It's a direct prediction without parameters. And it also predicts that the even and odd multiples will be different by some amount. So this is the data, this is the model, and now this is the prediction. So in the new predictions, you see that agrees much better with the observations. It's not perfect. For example, this is the octopole. The octopole, it predicts that it should be larger, and it's not as large as predicted. But given the big error bars, this is not a significant fluctuation. So you have to take all of these together and do a chi-square measurement for this. This will be something similar to the Bayesian, is the log of the likelihood function of the two models. We call direct sum inflation and standard inflation. And this is in log space. So you can see that direct sum inflation, the one that breaks the parity, has about 100 times larger probability than the standard inflation with the same number of parameters. The exact number we have qualified to be up to 650 times larger probability. Okay, so this is the parity map. So now I multiply the temperature by the antipodes. You can see here now the parity map with the mask. If you see a lot of blue here, it means it's antisymmetry. That's another way to qualify that. So we have qualified that in different ways and do a statistical analysis of that. And let me just show you the summary of this qualification, which can be summarized in these plots. This is the quadrupole. The quadrupole measured predicted by standard inflation is this red point here. The one measured by the cosmic macro background is the blue one. And the one predicted by the new theory is the green one here. So you can compare here the measurements. So basically the standard inflation, that's much poorer than this. And we quantify this there are some details on this, but I prefer to not bore you with details. There is a lot of statistical details. It's a 60-page paper. You can welcome to read and send me emails with questions about this. It's a lot of work that Shravan helped me doing. And let me mention, just to finish, the relation with other anomalies. This is one that is very well known. You might have heard about that. It's called the hemispherical power asymmetry. What this means is if you smooth the CMB map on very large scales and choose a projection in the ecliptic plane. So here is the ecliptic plane. So basically is the plane of our solar system. It turns out that the fluctuations on the north of the ecliptic plane are lower than on the south. And this anomaly has produced hundreds of papers, people trying to explain this, and has been called evidence for anisotropy in the universe. Okay? What we have found is that if you lower the quadrupole, this anomaly goes from being something like 0.5% to something like 15%. So it's very improbable in the standard inflation, but if you have a lower quadrupole, like in the direct sum prediction, the anomaly disappears because 50% probability is totally reasonable. 0.5% probability is not so reasonable. So basically, the biggest anomalies I already mentioned is this power asymmetry, the low quadrupole, and the other one is the two-point function that has this shape that is a bit funny, which I show here. The anomaly of the two-point function is usually mentioned to be less than 0.1%, and with a low quadrupole, we find it to be something like 9%. So some of the very well-known anomalies on large scales disappear when you consider this part. This is to announce some work that we have presented already here with Pablo Fosalva and with Benjamin Camacho, where we find these other anomalies, which is that cosmological parameters in different regions of the CMB sky are different. And I believe these anomalies could be related to this lack of power on very large scales that I mentioned at some point with the horizons. So I stop here and I thank you.
Okay, thank you very much, Enrique. Questions for Enrique or comments? To which school did you go? That they explain quantum mechanics?
Which is cool.
You mentioned that you do.
Roftarak
Roftarak is
explained to
yeah.
me.
I see. I went to the same school.
Enrique,
Question, I think one.
yes, I'll be brief. I have to leave. I like very much the seminar. Thank you, Enrique. So I have a question about the dipolar modulation. You know that there are these anomalies. If you look at the flows measured with supernovae or measured with quasars, no, or even radio sources, there doesn't seem to have the same magnitude. It has the same direction of the CMB dipole, but not the same magnitude. So do you think with your new insight, can we explain also this?
Yes, so thank you, Juan. Let me repeat the question. The question is that the dipole that I mentioned, when people try to, you can deduce the dipole, which is our local motion from the CMB, and then compare with other measures of our local motion. There are several ways to do that. And in the recent years, there has been several papers claiming that they don't agree. And this is another anomaly. In principle, it's not fully addressed by our analysis, but I just want to mention something funny that in fact we include in the paper, that the dipole is an odd, the dipole is an odd one because it's L equal 1. So the dipole should be larger. So the primordial dipole, according to this theory, should be larger, but still, even with the numbers that we put, is not comparable to the dynamical one. So it doesn't really, this theory doesn't address this problem, one. I think this is another issue that needs to be looked into.
Okay, thank you.
Thank you.
Thank you very much.
Maybe I'll give you one. It's a confusion I have sometimes, like in the definition of parity. Like, because it's like the parity definition that you gave is the parity of the mass, right? And so I was wondering, how is this related, and if it is related to the parity of the fields, so of your theory?
Yes.
Like if you have a model of inflation.
This is a very good question. Yeah, we get a lot of this. There is a lot of literature about parity violation. We call this parity asymmetry. In parity violation, what it means is that you can add terms to the Hamiltonian or the Lagrangian of your theory that use pseudo-scalars instead of using scalars. And pseudo-scalars have exactly this antisymmetric property that instead of they are reflected. So these parity violation terms produce some effects. For example, in the power spectrum, in some measurement, not in the power spectrum. Usually, it has to be high order correlations because they relate. So in this case, it will be like some shape you can define that when you change the parity of that shape changes the measurement. For example, for the 2-point function, this doesn't happen unless you are at antipodal regions. So in principle, the short answer is that there is no relation with these additional parity violations. This is more global. This is just saying that the whole structure, the geometry that you have this parity and not terms in the language.
But then I don't get what you learn on the theory with this asymmetry, right? Like, is this telling you, because at the beginning you said that this may be useful for quantum gravity?
Yeah. I didn't explain this at all. This is a lot of work done by Sravan and collaborators, where basically the proposal is this direct sum idea that you have to go back to the basic Schrödinger equation and change it so that it preserves this PT symmetry, rather than now that it chooses a time direction. And this creates a lot of problems. For example, this was realized by Schrödinger, by Einstein and Rosen. For example, the famous paper of Einstein and Rosen that people attribute to wormholes, to the creation of wormholes, really is addressing this problem. It's addressing the fact that if you choose it in your equation in time, then suddenly there appears to be two spaces that are disconnected. And that's where the worm the wormhole idea came. In this scenario, what we're saying is that there is, in the theory, you have this PT symmetry, which means that time here, we put TP, is a parameter. It's not the time that we use in classical dynamics. And in this theory, when you put this PT symmetry in the Schrodinger equation, what you have is that the field, the wave function, has a parity mirror in the other side that is going back in time, in this time. So basically, to make the theory TP version, the field in parity conjugate regions is evolving in the opposite time direction. And this sounds a bit strange, but this is in fact the way you can make the theory PT. And it's not strange when you think in quantum field theory. For example, in the Feynman diagrams, or in the
Dirac equation.
Exactly, even in the Dirac equation, you have this is how antiparticles were detected. So this is the same concept as antiparticle, but instead of going to the Dirac equation, you do it at the lower level of the Schrodinger equation. That way you can modify inflation and make a prediction. So that's where we see this connection, but this is not accepted by the community. It's just a conjecture. And so we are trying to find other evidences for that. There is other possible evidences for that, and this is what we're working.
Question, because I think we are a bit late.
Thank you. Are there any other predictions of DSI where we can observe large-scale surveys?
Yes.
Other than CMB?
Yeah. I mean, this is this is another thing we've been doing, thinking about that, finding new ideas, and also trying to relate this with these black hole scenarios ideas. There are some connections between the two things, because this is precisely the problem of crossing the horizon. This problem appears when you cross the horizon, is basically when a quantum fluctuation becomes classical. And that's where this asymmetry appears. So there are aspects we are exploring where this could be. In fact, today, Mireia in our journal club, no, in our group meeting, mentioned a fuzzy dark matter. Fuzzy dark matter is quantum dark matter. It's a dark matter that has very low mass and has a quantum wavelength that is making the whole halo a quantum state. This could affect fuzzy dark matter, for example. Polarization of the cosmic microwave background. If there is parity asymmetry in the temperature, it should also show in polarization. Large-scale maps of galaxies. We believe that also you can see that, but something we've been working with in Hamil, but it's challenging. So you are in a regime where the errors are very large, and it's something difficult to measure, but we don't fully understand all the consequences of this. But it's a very clear evidence. It's very hard to explain this parity asymmetry in CMB or in any other way. Nobody has provided a theory for this.
Second part of question is, have you checked the cold spot region of the CMB?
Whether
Something to do with
no, we haven't, but you are welcome to check. See, so by our now learned skills here, the hotspot region usually there is a very hot one called here, but it's in the middle of the galaxy. I think the one you mentioned is here, no?
I think the one below.
The hot or the cold?
Cold.
This one. Okay.
Yeah.
So the parity symmetry of that. So this is this one. So it will be this one. Yeah. So it's hot. Right? You can see here.
Okay, maybe we can continue on discussion in the pizza. So let's thank Enrique again.